So today, I'm going to spend a few brief moments with you talking about databases. Now you might be thinking to yourself, oh dear God. First off, that sounds geeky. And secondly, what do I really care about databases? Well, on the first topic, sorry, it is geeky. There's nothing I can do about that. But on the second part of the topic, something you may or may not realize is that you interact with hundreds of different databases during the course of an average day. When you go to the ATM machine and you put your card in the slot and you type in your little PIN number, there's a database that are putting those two pieces of information together and allowing you to get your money out. When you go to the grocery store and you make your purchases and you have your frequent shopper card, there's a database that's recording that you're there, that you're purchasing from that store, that you're doing it at that time, and what you're actually buying, which in all honesty is a little bit creepy. Okay, until you realize that that data is used to make sure that the things that you want to buy in the grocery store are there when you want to buy them. Later on in the evening when you go out to dinner, you pay for that meal with a credit card, and that credit card company then remembers that you went to that restaurant at that time and you spent that much money, and they will use that information to send ads to you that are tailored to the specific things that you like. When you go home that evening and you can remember that J.K. Rowling just wrote a new book, but you can't remember what the title is, and you log on to Google and do a quick Google search, Google has a massive database that they use to answer that question. When you log into Amazon to go ahead and buy the actual book, Amazon will say, hey, you bought all the Harry Potter books, now you're buying J.K. Rowling's latest book. Other people who did that, they also like this other author. Maybe you should check them out. That's another database at work. Okay? When you get up the next day, same thing's going to happen. Our lives are intertwined with a variety of different databases. So it's important for you to understand how databases work. So let's talk about databases for a brief moment. What is a database? Sounds like a good place to start, right? Well, a database is simply just a piece of software. And it's just simply a piece of software that allows us to manage a set of data and allows us to ask a series of questions to that data and get answers. So, this is something that can get pretty boring pretty quickly. So let's, instead of getting boring right off the bat, let's go with an example. So a good example of something that has to do with a database is your home address. So if you think about it for a brief moment, an address, we like to think of an address as a block. Yeah, this is my address, right? Well, let's break it up. Okay, and break it down to its individual components. It turns out that a home address probably has about 5 components to it here in the US. You're going to have the street address. Potentially you're going to have an apartment number. You're going to have the city, the state, and the zip code. So there's 5 components to it. Databases love information like this. Now if my home address was going to be put into a database, first they would create what's called a row. Okay, that's the Jim Anderson row. Then on that row, they would put the different components of my address. And for each component of it, they would create what's called a column. So there would be a column for the street address, a column for the apartment number, a column for the city, the state, and the zip. So hopefully you have a good mental impression of what a database sort of looks like. It's a series of rows for each one of the addresses, and then it's a series of columns for each component of the address. It's no more complicated than that. So, how would you actually use an address? Well, let's say, so my address is now in the database. Let's put your address into the database. That means we'll create additional rows. In fact, let's put everybody in the local areas, name and address, into our database. Well, we've got a pretty big database now, right? Tens, maybe even hundreds of thousands of rows in our database. But we still only have 5 columns, right? Well, great, we've got a database. Cool, we're all done. Well, that's, building a database is a lot of fun, but really that's not the power of a database. The power of a database is being able to use it. Let's say that you own a grocery store here in town, okay? And oops, something went wrong. You've got way too many tomatoes. You've got to get rid of the tomatoes before they go bad. Well, what are you going to do? Well, what you'd like to do is send out a postcard to everybody who lives in the area around your grocery store with a recipe that calls for a lot of tomatoes, okay? Now, a little trick to this is you don't want to send that out to everybody in town because everybody in town isn't going to shop at your store. You only want to send it out to the people who live close to your grocery store. Well, a lot of different ways to do this, but a simple way is everybody who's in the same zip code as your grocery store would be a great person to send this postcard to. So you could go to the database that we just created and say, hey, I would like you to give me a list of all of the people who have an address that has the same zip code as my grocery store. You know, that's the kind of thing databases do really well. Poof, you get your list, and then you could send your postcard out to all those people. Poof, that's it for databases. And you would think that that'd be the end of the story. And in fact, it was the end of the story for about 40 years. So databases in their current form were invented probably in the 1970s or so, and they did a great job up until the early 2000s. Then we ran into a problem. And the problem that we ran into was that the data that was going into the databases just got too big. Okay? In fact, there was a little company at the forefront of this problem, and you may have actually heard of them. They're called Google. Now, Google's goal was to index the World Wide Web once a day. Now, back in the early 2000s, that web thing was pretty big. Guess what? It's just gotten larger since then, right? So Google realized right off the bat that a traditional database running on a traditional computer wasn't going to be up to snuff. It wasn't going to be able to do it. So they've got really smart people working at their Google place, and they put their brains to it. And they came up with a solution, and it's a cool solution, okay? And in fact, it was so cool they couldn't keep it inside. They had to publish technical papers talking about how they did it. So in 2002 and 2004, they published 2 separate papers that explained how the Google system for indexing the web once a day worked. There's a gentleman named Doug Cuttings, who was working at the time, and he was actually working on a project that was designed to create a crawler that was going to crawl the entire internet and visit each website and get the data off of that site. Sort of like Google does, but more of a low-key type of deal. He read these papers, and like a light bulb went on in his head. He said, wow, you know, the technique that Google has created, I bet with some modifications, I could use that to build a brand new type of database system. In fact, a type of database system that can handle an almost unlimited amount of data. I would solve the problem that everybody's having, where basically their databases are just getting too big to use effectively. So he sat down, he went to work, and he came up with a solution. The solution that John Cutting created is called Haddop. And whenever you're talking about Haddop, the very first question you have to tackle is,
why the name?
Why is it called Haddop? And that's a good point. It's actually an anagram that, no, it's not. The reason it's called Haddop is because at the time, his young son had a stuffed elephant, and he called that stuffed element Haddop. And so his dad, who was working on the software project, decided he was going to call the software project Haddop. And it's no more complicated than that. All right. So once again, when we're going to be talking about databases, it can get very boring very quickly just to talk about databases. So instead, let's talk about a problem, because our problem's a lot more interesting. So let's talk about U.S. Census data. Census. Now the census is taken every, is it every 10, 12 years, something like that? What happens is people go out and they knock on your door and they ask you a series of questions. Now in the United States right now, there are 360 million people living here. And let's say those people who come to your door ask you 100 questions. Wow, that's a database, isn't it? So it's going to have 360 million rows, and it's going to have 100 columns. That's a big database. Now remember that little computer that we talked about that was doing our name and address thing? So if it was even possible to load that database into that computer, you could sit down on Monday and ask it a question, and then go away, and then like Friday, when you came back, it might have an answer for you. But it would only be your answer. So if multiple people wanted to ask it questions, give it up, right? So right off the bat, when we're dealing with a really big database, we've got a fundamental hardware problem. But good news, we can solve all hardware problems with faster hardware, right? So get a supercomputer, and your database problems will... That's actually not true. When you're dealing with database problems, part of the problem is that it takes so long to get the data that even processing it isn't necessarily your bottleneck. You've got storage, you've got network, and you've got processing, and you've got memory. You've got bottlenecks all over the place. You can't even walk across the room. You have so many bottlenecks. All right, so a supercomputer, first off, is very expensive, and secondly, won't solve the problem. Well, that's where those guys from Google came in. They actually came up with a clever solution, and we're going to take their solution and apply it to this problem. So in the world of Haddop, what you need is you need a processor. Ideally, a cheap processor. You need memory for that processor. Ideally, cheap memory. And you need a disk drive. But as long as you have a disk drive, you may as well have 10 disk drives. Well, as long as you have 10, you need 100 disk drives, right? Processor, memory, and 100 disk drives. We're going to call that a node. Well, once you've gone to the effort of building a node, it seems like you could probably build another node. And you could probably stack it on top of that. And once you do that, you can do that again and again and again and again. Once we've got a stack of nodes, let's call that a rack. Okay, we've got a rack of cheap computers. Well, once you've built a rack, why stop there? You can have rack after rack after rack. And let's take a group of racks and let's call that a cluster. So a Haddop computer, the one that's running the Haddop database, is a set of clusters. The really cool thing about Haddop is as you get more and more data, all you have to do is add more and more clusters. And you're able to process more data. And remember, these are cheap. You go into the dinged and dented, you go into the discount part of the hard drive store and you're buying this stuff. Because you have so many of them, none of them cost that much. All right, so let's come up with a problem that's well suited to our brand new Haddop cheap computer that we bought. We're dealing with census data, right? Okay, so here's the problem for you. I would like to know how many families in the United States of America make $1 million or more per year and have more than 10 children. Valid question, right? Can't be that many people. But now I got to go search 360 million records and check on how much they make and check on the kids. Whew, this is going to take a little while to do. All right, so I'm going to need a bunch of clusters to do this. So I would like you to be my Florida cluster. So all the census data for the Florida is going to be stored on this cluster. I would like you to be my Texas cluster. So all the information on Texas is going to be stored there. And Joe, I'd like you to be my California cluster. So we've got 3 separate clusters for our Haddop system. Now admittedly there'd be another 47, and that's all fine. We've got no problems with that whatsoever. Now the Haddop system solves this complex problem by using 2 separate components. The first component is called the Haddop Distributed File System, which is great because when you're at your next cocktail party, drop that little gem on whoever you're talking to, and the conversation is over at that point in time. So really, it's a fancy name, but here's the gist of it. When you've got a massive amount of data, the question is, where are you going to store it? Well, excellent question. Now, if you tried to put it on a single computer, very quickly you're going to have too much data for any single computer to process. So, right off the bat, we can say, well, we got to do is break that data up. Great, not a problem. 1,001 different ways to break data up. The way they break it up in a Haddop system is they come up with a concept called a storage unit. I'm going to get geeky. I apologize. A storage unit is 512K bytes in size, which is pretty small. Now, storage units all gathered up into something called a file unit. Geeky again, sorry. A file unit is 64 meg in size, and file units is what Haddop deals with. So what it's going to do is it's going to take your US census data, break it up into a series of 64 meg chunks, and then it's going to distribute it out among the different clusters. Here's where things get really interesting. I'd like to remind you that the clusters that we built were cheap. Now, cheap means what? Cheap means we're going to have failures. Things are going to break. We didn't really get a Mercedes here, okay? We've got more of a Yugo type of system. But the Haddop designers realized that from day one. So what they said is, hey, listen, when you put your data on a cluster, we're not just going to put it there once. We're actually going to put it there multiple times. In a Haddop system, the default is 3. So each file block, each 64 meg bit, is going to be stored 3 times. What that means, if any component, any node of it fails, I'll have 2 backup copies. No big deal. I can go on. Okay. So now we've solved our storage problem. You need a lot of storage, right? Because it's your database times potentially 3. But that's fine. Disk drives are cheap. No big deal. Now, our next challenge is how are we going to answer our question? What's our question again? How many families in the United States have more than $1 million from each year of income and have 10 children or more? Okay? Well, we want to get our question answered. Well, what we're going to have to do is there's another part of Haddop called MapReduce. This is a cool piece of software. What this does is it takes your question and then it farms it out to each cluster. It says, hey cluster, with the data that you have, see what the answer to this question is. So, for our Florida cluster, what would the answer be written on that sheet of paper?
5.
5. For our Texas cluster, what would the answer be?
10.
For our California cluster, what would the answer be?
20.
20. Excellent. So now each cluster knows their answer. Now one of the clusters is picked basically to be the boss cluster. Joe, you're the boss cluster. And all the other clusters pass the results of their query to him.
Thank you. Thank you.
Now the boss cluster at this point in time says, hey, I know it all. But this, these individual values, that's not what the person asked. And the boss cluster uses its superior computing power to come up with a final answer. Joe, in the United States of America, based on the latest census data, how many households are there in basically Florida, Texas, and California in which their household income is over $1 million and they have 10 or more children?
That's going to cost you more storage. 35.
35 is the answer. Poof, and we're done. Now, an interesting thing about this is because the data is stored on each cluster in a fixed size, 64 meg, right? The amount of processing time it takes on that node is exactly the same. So because you've distributed the task and because the data is the same size, it gets done lickety-split. You ever do a Google search?
Mm-hmm.
Google would come back pretty quick? Haddop works. Okay? So this different approach to databases is being used today in the financial industry to do fraud analysis, because that's a bummer to do. You need a lot of data for that. In the biotech field, to basically do a lot of stuff with genomes and stuff like that, and also to do it in the retail field, to figure out what products to provide to what people at what times. So Haddop usage is predicted to be 50% of all database usage by the end of 2015. So this is a brand new way of doing databases. It's a brand new way of dealing with big data. And now you know everything you need to know about Haddop.
You might be asking yourself, where do I go from here? The ability to effectively manage an IT department and to do it well is a skill that your company needs you to have. It sure makes sense to invest the time and energy that it takes to become a great CIO. A simple way to start doing this is to sign up for the free The Accidental Successful CIO newsletter. This monthly publication is sent to your inbox and is overflowing with tips and techniques on how you can spend your time making the right IT decisions and really leading your department's IT professionals. We'll cover how to evaluate new technologies, how to foster relationships with other parts of the business, how to hire the right staff, how to work with the CEO so he understands just how critical IT is to his and the company's success, and we might even cover a few CIO career tips or two. Hey, the newsletter is free, so you can't go wrong there. In the description of this video, you'll find a link that you can click on. Go ahead and click on it, and you'll be taken to a web page that will let you sign up for the newsletter. There's even a free gift in it for you when you do. Thanks for watching this video, sign up for the newsletter, and congratulations on starting your journey to accidentally becoming a successful CIO.
Thank you.